Welcome to a course on set theory, logic, and inference. My name is Adam Pease. I'm going to be your instructor for this course, so let's get started. My interests are primarily in logic, ontology, theorem proving, and also symbolic applications of natural language processing, as opposed to the more statistical methods that are more prevalent today. I'm probably most notable for being the author of the suggested upper merged ontology, which we'll allude to during this course, although it will not be the focus of it. And you can find out a lot more information about me at my website, adampease.org. I also want to mention that most of the slides of this course were quite generously provided by Stefan Schultz, a longtime colleague and collaborator of mine, and also a colleague of his, Jan Hladek. So maybe the first question to answer is, why study logic? What is it about? What is it for? Why should we care? Well, it is, I would contend, absolutely central to computer science. Logic is necessary to understand what computer science is about. It's fundamental. Now, of course, you can be a coder, a hacker in old terminology, without knowing anything about logic in particular. You can just practice the mechanics of programming and certainly be very effective at it. But I would contend that knowing something about the underlying mathematics of computer software and computer hardware is a beneficial thing. And then, of course, there are also lots of applications of this technology. As an analogy, you can certainly drive a car without knowing about engines, but it's certainly nice to know a bit about what's going on under the hood, so to speak. So you need to know about theoretical foundations of computer science if, for example, you want to understand what's going on at the hardware level, which is governed by Boolean logic. So transistors and so forth operate in accordance with the rules of Boolean logic. And most of programming does have some use of logic. Your if-then statements, obviously, are conjunctions and disjunctions, ands and ors. And there are many applications that inherently need an understanding of logic. If you're doing some parallel processing, understanding a communication protocol, for example, make sure that it doesn't have deadlocks or live locks. Boolean algebra, theorem proving can help with these things. And also understanding how certain logical formulas can be reduced to other logical formulas gives you an opportunity to optimize your code, make sure that your code runs as fast as possible. A higher level application is verifying programs to ensure that they're correct. There's a lot of exciting research going on in this area and a lot of exciting application. So companies like Amazon and Microsoft do employ people that are working with logic and theorem proving to try to prove that portions of their systems are correct. And especially if you have high risk, high trust, sort of high consequence systems, certainly in applications like cybersecurity, you don't want the hackers to get into your system, find ways to sneak in and violate your protocols, violate your software. Or if your software is running something that has a potentially big impact, maybe on human life or human safety, things like space systems, for example, or military systems, it's essential that they perform as required, because the consequences of a mistake in the software, a bug in the software, could be an issue of life and death. And a lot of my commercial work, my commercial consulting work in the past, has been in modeling data and metadata. There are large companies, multinational companies, that have very, very large databases, and over time, it's been my experience that these databases keep growing and they get less and less consistent as more people touch them, because there's not a lot of automation, at least in the state of the practice, that can be brought to bear to keep databases consistent. But logic and also ontology, which I'll allude to several times in this course, has the potential to keep things consistent, to apply automation, to ensure that data and data definitions and data instances are all being used in the way they were intended, the way they were declared. And that's more than just doing static typing, for example, in a language like Java or C++. There's a lot more that we can do to ensure that our data is correct and consistent, and logic is, I believe, the way to help with that. And I'll show some examples of that over the course of this project here that we're talking about. All right, so let's get started with a little bit more of the background. So we're going to need to have some vocabulary to talk about the things in this course. And in fact, some famous linguists, Sapir-Whorf came up with this hypothesis: language determines thought, linguistic categories limit and determine cognitive categories. I believe that's certainly true about formal languages. I'm not convinced that's true about human languages, since they're all roughly equivalent in expressiveness. But it's certainly the case for formal languages. If your formal language doesn't let you say something, or doesn't let you say something easily, it's going to be very hard to make that a part of your development process and to understand kind of at a deep level what you might be leaving out in your declarations. As programmers that are experienced in conventional languages like Java or Python, we don't have a language for data description, static data description, other than typing. And I will attempt to show at various points how that leaves out a lot of information that we could be capturing to our benefit and helping our software work well. So we're going to need to talk about how do we speak about arguments, logical arguments, understand what it means to have a proof or an argument that is verifiable and correct. How can we describe algorithms and data structures and programs abstractly? How can we express natural language constructs that also express mathematical things, so like high school word problems, for example? And how can we turn those natural language expressions into formal expressions that a machine can help either compute or verify, or maybe even both? And we're going to need to talk about notions of syntax, semantics, interpretations, models, truth, validity, derivability, and many other things. So we'll be defining all these concepts as we go along, because they're integral to understanding logic and how logic works. Another quote, thanks to Ludwig Wittgenstein, the limits of my language are the limits of my world. I think that's an even more pithy quote than the Sapir-Whorf hypothesis. I'm going to attempt to help you develop a bit of mathematical and methodological competence in logic. We're going to learn how to model systems with abstract tools. We're going to talk about the applications of logic and deduction. We're going to figure out how to create arguments using logic and using deductive methods, and also create arguments about programs and their behavior. Here's the overall schedule that we'll follow. First is just our introduction that I'm doing now. We'll talk next about a very simple inference system to kind of get you the feel of what it means to do logical inference, but in a much simplified mathematics than full logic, full even propositional or propositional logic or propositional calculus. We'll talk about set theory, because it's really one of the foundations of logic and computing as well in general. We'll talk about numbers, algebra, set operations. Then we'll move on to graphs and relations and functions, the cardinality of sets also. Then finally, we'll get into an actual logical system, the first logical system that most people learn, propositional logic. It's the most straightforward, but it sets the groundwork for first-order logic, or predicate calculus is another name for first-order logic, that will come later in the course. It allows us to have a system that doesn't force us to talk about so many details right from the start, and I think that's a helpful approach. It's fairly typical also for when people are teaching logic. We'll talk about the notion of semantics. How do we interpret the meaning of the symbols and the symbol systems that we're constructing? Also, what's a model? What's an instantiation of our variables or our symbols that makes a logical system true? And validity. How can we determine that we're doing our work in a system that preserves truth. If we start from truth and we do things that are true, that are truth-preserving operations, do we also wind up with collectively a true system? That's really what validity is about. We'll then start getting into a couple of methods for doing inference. The first one is just truth tables, a very straightforward approach that everybody starts with, and hopefully this will give you some grounding in how to understand that the operations that we're doing and the logical operators that we have are actually true and legitimate. We'll then talk about the tableau method. It's a bit more complicated in terms of doing inference. It's also something that can be easily automated and is a bit more efficient in many cases than truth tables, and we'll explain why. We'll talk about formulas and parts of formulas, how to do substitution from one formula to another, usually with the objective of simplifying things, and normal forms is a particular powerful and ubiquitous way of reducing complicated logical expressions into simpler logical expressions so that they can be used more easily in an automated theorem-proving system. Then we'll get to resolution, the primary algorithm that is used for theorem proving in first-order logic, but we'll start off talking about it in propositional logic. We'll talk about saturation, the process of applying resolution theorem proving to try to find an answer, and then we'll give the details of first-order logic. So we'll finally, at that point, expand our logical system that we're working with some new operators that allow for more general and more complicated things to be said in this formal truth-preserving system. I'll spend a bit of time talking about quantifiers because those can be a challenge to understand fully when you're getting started in logic. Along with that, we'll have a very brief introduction to ontology, to how one can collect a lot of logical statements in order to have a description of our world. I'll also talk about then classes, taxonomic structures, how do we arrange the things that we want to talk about that do model the world into a coherent structure, things that are more general or more specific than one another. I'll touch very briefly on higher order logic, just so that you know what it is. We won't do any inference in higher order logic. I'm certainly not an expert in higher order logic, but it's important to mention where are the boundaries of first order logic. This is a common thing that I think can be challenging for programmers to grasp because we're all used to performing our work in languages that we might say are more convenient, maybe than one is more convenient than the other, one is a language we're more familiar in, but we're not totally limited. We work in Turing-complete languages, most of us, I think the vast majority of us, and it's possible to do just about anything in any language, just maybe it takes a little longer or it's a little less elegant or something. That is just not the case in mathematics. There are hard limits on what one can say and then the computational properties of what one says. So understanding where are the boundaries of propositional to first order and then beyond first order is really important for making intelligent choices by what modeling languages and what inference systems we might use on solving a particular problem. And also touch on a few examples of practical reasoning in determining facts about time and about space. So that's the planned schedule, and we'll try to take it in small bites, and hopefully you'll enjoy what's to come. So the first thing that I want to do as an exercise is introduce a very, very simple formal system, but I'm going to introduce it semi-formally, just in natural language, and then we'll make it a bit more rigorous. So imagine this following formal system that has just a set of letters, and we're going to be doing manipulations with strings. All words that we have consist of combinations of the following three letters. We have a letter M, a letter I, and a letter U. The first rule that constrains the use of those letters is that if a word ends in the letter I, one can append a letter U to it. So you can turn one statement in this formal system into another using this inference rule. A second inference rule is if you have three I's at the end of a sentence, you can replace them with a U. Not add to the end, but take away those three and replace them with a U. A last rule here, or actually a third rule, is if you have two U's anywhere in the string, you can remove them entirely. Fourth rule is that if you have any sort of a combination of letters after an initial M, a letter M, you can double them. So if you have MI, you can create MII, and so on. It's rules 2 through 5 tell us how we can transform one string in our language into another string. Rules 1 and 6 constrain what strings exist in the language prior to transformation, and also they're also true after all these transformations. So the last one here is a derivation. Any problem, any system of strings in this language always starts with MI. So you'll find that there's no way to get rid of that first M. There's no way to add any more M's to the system. You always have an M that starts out. So really we're going to be about manipulating I's and U's. And this is a problem, a system that is all thanks to Douglas Hofstadter and his wonderful book Gödel Escher Bach, An Eternal Golden Braid. That was a book I enjoyed very much. It's a fantastic intellectual romp through all sorts of different issues, puzzles. I'd really encourage you to at least give it a try. It's a lot of fun. We're going to have some notation that we need to introduce along with this system of strings. A turnstile symbol that you can see here is a derivation step in our formal system. We can also put a subscript on it that says which of our rules is being used. So as you've seen, we have rules 2 through 5. We have 4 different rules. We might renumber them 1 to 4. It'll be a little easier to remember, I think. If we have a superscript on our turnstile, it says how many steps are used. So we'll number the steps sometimes with a superscript. We'll also use an arrow to describe rules. It says we can go from from having one string into another string. So it indicates a substitution that may be performed. Keep in mind, this symbol exists in many different systems. I'm just introducing what it means here in this very restricted system. We'll also have a cardinality operator. That's a pair of vertical bars. So you might have seen that in very simple introductions to high school sort of mathematics. It's a common operator, and so it just means it's a count of the number of characters in our case. So if you have MI, the vertical bar operator would yield the number 2. And we also have a modulo operator to describe some interesting properties of our system. So now we're ready to talk about our system in a more formal manner using the notation that we've introduced. So again, all words in our system consist of just 3 letters, an M, an I, and a U. We can have variables. So let's have just X and Y. Those are really, we really only need 2 variables, and we'll make them lowercase so that they stand out visually or typographically from the rest of the characters in our system. A derivation always begins with MI, so there's no way to get rid of that letter M. All of our strings will start to M. We're really just talking about modifications, transformations, derivations that are with the I's and the U's that follow that M. There are only 4 derivation rules. If we have an I at the end of a string, we can add a U to it. Our second rule is if we have 3 i's in a row anywhere in the string, and this means that this rule could potentially be applied in multiple ways in a given string if you have lots of occurrences of 3 i's together. But any place you do have 3 i's together, you have the option of replacing those 3 i's with a u. If you have 2 u's anywhere in the string, then you can just eliminate them. And like rule number 2, rule number 3 can also be potentially applied in different ways in longer strings that might have multiple occurrences of 2 u's together. Finally, there is a rule that we can double anything after the initial character m. We can write each of the steps in our derivation with the turnstile. And here's just an example to follow along with. So if we start with mi and we apply rule 4, which doubles the characters after the initial m, then we get mii. If we apply that rule again, so it's rule number 4, then we get 4 i's after the m. Then we can choose to apply rule number 2, and we're going to apply it to the pattern of the first 3 i's. If we applied it to the later 3 i's, we would have gotten a different result, obviously. So here we're going to replace the first 3 i's by a letter u to yield mui. And then we can apply the fourth rule again, and that gives us mui. So here's just a sample derivation. So you might be asked, how do I transform my initial word mi into another word, mui. And then it would be up to either you or the software that we will write as an exercise to transform the first statement into the last statement and report how you did it, or how the program did it. So again, rules 2 and 3 can apply several ways to the same string if the string is long and complex enough and has multiple instances of those patterns. And the variable y can be empty. So if we have, for example, muu, right, then y is nothing if we're trying to apply rule 3. All right, we turn muu into just m, and the x is matching an m and the y is matching nothing because it's at the end of the string. So the exercise that I'd like to suggest that you try is the following. We've got 4 different strings. Start with mi and see if you can derive muiu. That one is relatively simple. Then see if you can derive one with 5 i's after the m, and then 3 u's and an I. That one's a fairly long derivation. And then there's a trick question, mu, that you can't actually derive, but see if you can play around with it and get a feeling for why that's impossible. And then we'll talk a little bit later about how we might be able to prove, in fact, that it's impossible. So give that a try, and we'll come back in the next video and talk about the answers.